Hello, welcome back to another video of Math of the Day presented by Jude Didelot. It is currently June 4th, 2025. Today we'll be learning about sigma notation, and sadly, it has nothing to do with the brain rot term. But I say, let's get into it. Here, I have this weird expression. This symbol that looks like a weird E is actually a Greek letter. It is the Greek letter sigma and translates to the English letter S. As you can see, there are numbers on top, below, and on the side of sigma. These numbers have special meanings. The bottom part is known as the lower limit, and it represents the starting value of the variable n, which is 1. The top part is known as the upper limit, and it represents the last number n is equal to, which is 5. And this part right here is our argument or rule that we follow, and we plug n into this rule. So when we solve this expression, we first apply this rule to n, and we add it to all the rule applied numbers above n until we get to our ending point, which is 5. So you'd plug in n for 1, 2, 3, 4, and 5. And you would substitute n's value for n right here, so you do 2 times 1, and so on. So sigma is also often referred to as summation because we add all of the numbers applied to the rule. Since n is equal to 1, we will follow our rule 2 times n. This means we must multiply n by 2, so we have 2 times 1, which is equal to 2. Since we're adding, I will put an addition symbol here. So now let's apply our rule to the next number. The next number is 2 because each time we add 1 to n to find the next value of n, we apply our rule to. So 2 times 2 is 4. Then we have 2 times 3, which is 6. Then 2 times 4, which is 8, and finally 2 times 5, which is equal to 10. Oh, sorry about that. See the pattern of the numbers that we're adding? Because each time we add a new number, that number is 2 more than the last. 4 is 2 more than 2, 6 is 2 more than 4. This means that this addition problem is something called an arithmetic sequence because an arithmetic sequence increases by the same number. In this case, it is 2. But first, let's add our numbers. 2 plus 4 is 6. 6 plus 6, this is 6 plus 6, which is 12. And then 12 plus 8 is equal to 20. And then 20 plus 10 is 30. Sorry if my addition was kind of confusing. I just kind of made that up on the spot. But basically 2 plus 4 plus 6 plus 8 plus 10 is 30. So the answer to this expression in sigma notation is 30. The reason I pointed out this arithmetic sequence is because there's another way to solve this problem. It is by using the formula the partial sum, or S sub n, of the sequence is equal to the first term, or a sub 1, plus the last term, or a sub n, divided by 2, which is all multiplied by the number of terms. In this case, the first term is 2, so let me write this out. First term is 2, and the last term is 10, because we can see this right here. This is our first term, and this is our last term. So 2 plus 10, all over 2, and then this is multiplied by the number of terms that we have. And the number of terms that we had in the sequence was 5, because we went up to 5 numbers. So we can put the 5 here. So 2 plus 10 is 12 over 2 times 5. 12 over 2 is 6. So now we have 6 times 5. 6 times 5 is 30. This is the exact same answer that we have here. The formula is very helpful because what if your upper limit was 100? If you were using sigma notation, you would have to apply the rule to all the whole numbers from 1 to 100, and it would be very tedious. This is where the partial sum formula comes in handy. We already know that the first term is 2, but what is the last term? The 100th term. To find this out, we can make n 100 and plug it into our rule. So, if our rule is 2n and our last number is 100, then we would just do 2 times 100, which is equal to 200. Now we can apply our formula. So let's write our formula out. 2 plus our last term would be 200 because we just figured that out. Oh, I almost forgot that parenthesis. So 2 plus 200 over 2, and then the number of terms that we'd have would be 100 terms because we have 100 different numbers that we're applying this rule to. So we would have 100 right here. 2 plus 200 is 202. 202 over 2. Let me write this out. Times 100. Alright, 202 over 2 is 101. 101 times 100. That's easy. You just move the decimal point twice over to the right, and now you have 10,100. This means that our answer to this partial arithmetic sequence is 10,100. This is much faster than using sigma notation if the lower and upper limits have a large range, like from 1 to 100. Imagine if it was 1 to 1,000. That would be really easy to calculate right here. This is as far as we will get for today. Next time we will apply a new sigma notation expression and learn about geometric sequences. Thank you for tuning into Math Today. I hope you learned something new. I will see you in the next one, and goodbye.